Hello, everybody. I'm very glad to attending this conference, although online. My name is Giovanni Bordogna. I'm a co-founder of Blue Wasp Marine, which is a consultancy fully specializing on wind-assisted propulsion. Today, I'm going to present a research which I carried out during my PhD studies at UW. So, has nothing to do with or little to do with my current job, but it's actually a research which I carried out during my PhD research at the Delft University of Technology in the Netherlands. So the title of the presentation is Performance Evaluation of a Flettner Rotor with Flap. So what happens to the performance of the rotor when we add a flap to this device? I would like to give a little bit of a background and preface to the presentation. As I just mentioned, the results obtained, the results that we present today were obtained during my PhD research at UW, which I carried out from 2013 until 2020. I also want to give credit to Albert Reikens and Nico van der Kolk, who contributed to the results which we present today. After I left UW, there was a period of about 3 years in which the university did not carry out any research on wind-assisted propulsion, but they start a new very large research program on this topic in 2023, and now they have several PhD students and master students working on this topic again. As I mentioned in the beginning, the company I co-founded and where I work at the moment, Blue Wasp Marine, does not produce Flettner rotors. So we have nothing to do with Flettner rotors, but it's an independent consultancy company fully specializing on wind-assisted propulsion, and we work with all wind-assist technologies available in the market. So before getting to the Flettner rotor plus flap concept, I just want to spend a few words regarding the Flettner rotor itself. As you might know, the Flettner rotor is a spinning cylinder that, thanks to the Magnus effect, generates an aerodynamic lift. So you have here on the right an image of the first ship which was equipped with 2 Flettner rotors, the Bacao ship, which crossed the North Atlantic from Europe to the United States. Indeed, the Flettner rotor is what we call an active device. So it requires some input power in order to spin. And by spinning, it generates a low pressure side and therefore an aerodynamic lift, which propels the ship forward. Today, there are several ships fitted with different type of Flettner rotors, from different manufacturers and different size. So the idea of adding a flap to the Flettner rotor was an idea of my supervisor, Lex Koning, during my master studies and PhD studies at UW. And the idea was to be able to control the separation points. And this basically means that you can also control the lift and drag production, and therefore also increase the lift over drag ratio, which is an important characteristic for all wind propulsion systems. So a couple of words related to the Magnus effect. You see here, let's say a rotating cylinder, rotating anti-clockwise. Here is a flow coming from the right to the left. And because of the rotation, you see that the flow is accelerated. So there is a low pressure side and therefore a generation of lift and also, of course, a generation of drag. So these are the forces that eventually will be generated by the Flettner rotor and will help the ship to generate a thrust and therefore to reduce the fuel consumption. Now, there is one fundamental parameter that determines the aerodynamic characteristic of a Flettner rotor, which is the velocity ratio, or also the key number. The velocity ratio is basically determined by the tangential velocity of the Flettner rotor divided by the incoming flow velocity. So basically, how fast the Flettner rotor is spinning related to the incoming flow velocity. Keep this parameter in mind because this is the parameter that determines the production of lift and drag of any Flettner rotor. So I mentioned earlier that by adding a flap, you can control the lift over drag of the Flettner rotor, and this is important for any wind assist device. And particularly, it's important to improve the performance of the wind assist device in when the ship is sailing upwind. And why is upwind particularly important for wind assisted ships? Now, this is what typically happens when a ship is sailing, fully propelled by the sail or by the rotor in this case. So you have here the Flettner rotor is producing a certain lift and drag according to these wind components. So this is a true wind direction, true wind speed. Here you have the boat speed, which is fully, in this case, fully generated by the thrust produced by the Flettner rotor. And here you have the apparent wind angle and apparent wind speed. So you see that the vectors of lift and drag are perpendicular and parallel to the apparent wind. Now, when we talk about wind assisted propulsion, actually it means that the ship is always in motor sailing mode. So it means that there is a component which is produced by the engine. Typically, the speed of the ship is fixed. Partly is produced by the engine and partly is produced by the wind assisted systems, in this case, the Flettner rotor. So what happens is that actually there is an increase in apparent wind speed, but also a decrease in apparent wind angle, which is detrimental. You see here that actually the lift component is pointing less forward, so the smaller portion of this vector is pointing towards the direction of the ship. So any improvements in the lift over drag ratio means that the wind propulsion system and therefore the ship is able to operate better in upwind sailing condition, which are the conditions that for this kind of ships occur by far the most frequently. So, as I mentioned, the results that I present today, they come from my PhD research. Here are the experiments which I carried out at Politecnico di Milano Wind Tunnel in Italy. This is a very large facility. It's about 40 meters wide, 3.73 meters tall, and about 36 meters long. So we tested the Delft rotor, which is basically was the spinning cylinder. The reason we tested this Flettner rotor was to understand the aerodynamic characteristics at full scale. So to understand whether the Reynolds number has an effect on lift and drag generation of this device. So there is a few more details related to the test setup. You see here now the rotor without the skin. The interior, we had a force balance at the bottom, a force balance at the top. We had a slip ring. We had an internal frame, which was rotating, of course. The engine, the electric engine, was attached here at the bottom at the lower balance. And then we had the skin with all the pressure tabs, horizontal pressure tabs, and vertical pressure tabs. So due to the this test setup, as you can imagine, basically the tip vortices at the bottom and at the top were suppressed by the ceiling and the floor of the wind tunnel. So now here are some measurements of the Delft rotor. So these are 2D measurements. Basically, these are results that were obtained at the pressure tabs at the center of the Flettner rotor. You see that there is an effect of the Reynolds number on both the lift and drag coefficients. So above a Reynolds number of 360,000, actually the lift coefficient, the effect of the Reynolds number of lift coefficient becomes quite marginal, whereas on the drag is still fairly large. So we decided to test the flap at the Reynolds number of 360,000 and not higher than this, because we wanted to reach a K value above up to 5. Okay, so the results that I will show you in a second related to the Flettner with the flap are related to a Reynolds number of 360,000. Now, here are some results still of the Flettner rotor without flap. This is the pressure coefficient along the Flettner rotor. 0 basically is this point. So here in this case, the flow is coming from left to the right, and the rotor is spinning anti-clockwise. So 0 is actually the point where the flow hits the Flettner rotor. 90 is this point, 180 and 270 is this point here. So here you see actually the depression that caused the generation of lift, and here is actually towards the rear of the cylinder, so this area, and this is actually where the drag is generated. So you see that for different Reynolds number, the pressure distribution is also different. And you can also, let's say, understand already that by adding a flap at a certain position along the Flettner rotor, you might able to, let's say, change this pressure distribution and therefore control the lift and drag production. So here is the Flettner rotor with flap. It was a very simple concept, let's say, and also simply made. It was a simple flat plate made out of plywood. Here on the picture on the left, you might think that there is, let's say, a large gap, but actually there was a plastic film that maybe you can see. Actually, the gap between the flap and the rotor was about 0.5 centimeter. Now, this flap, we could move it around by hand around the Flettner rotor at any position, as you might see here. So it was actually a very simple construction. The main purpose was indeed to set a separation point. Now I will show you a brief video of the rotor with the flap. You see the air is coming from right to the left. Here's a pitot tube. There are also pitot tube, let's say, from the ceiling, hanging from the ceiling of the wind tunnel. The rotor is spinning anti-clockwise, and indeed we could say separate, say fix the separation point with a flap and measuring the forces from using the bottom and top force balance, but also using the pressure taps at the center of the rotor. Okay. So here are some results of the experiments. This is basically what I showed you before. So the pressure coefficient along the position of the rotor, as you see here, 0 is again is where the wind hits the rotor. 90 is perpendicular where the low pressure side is. 180 is say at the opposite to where the direction of the wind. So in this case, these graphs show the pressure distribution using the flap at the position of 180 degrees. So this is actually the presentation of the flap. The blue indicates the pressure distribution without a flap, and the red color indicates the pressure distribution with a flap. So you can notice already that you can control actually quite well the pressure distribution. There is a reduction in lift, of course. You can notice, let's say, in this direction, but there is also a very nice and large reduction in drag. Okay, so there's actually no pressure pointing towards the drag direction, and you can see in the plots of the lift and drag and lift over and drag plots here at the bottom. So the black line with dots is actually the results without flap, and then you see the results for all the other flap position. So like in a nutshell, basically the flap can slightly increase the lift if you position it 247 degrees, so in this direction. But mainly what it does is to considerably reduce the drag. So you see that if you set the flap at 100 degrees, the drag is very much reduced compared to the case when there is no flap. So the lift over drag for some cases is actually doubled. So for example, for a K value of 2, you have without flap, it's about lift over drag is about 3, and using a flap is about you saw all the components which are taken into account in our performance simulations. So we solved, let's say, for the aero and hydro balancing 4 degrees of freedom. We take into account the interaction between the Flettner rotors themselves. we have the yaw balance, the production of side force, leeway. So basically all the components which needs to be taken into account when we deal with the sailing yachts, but also with the sister ships. So this is the case study that we evaluated. It's a Combi Freighter 5000 from Diamond Shipyard in the Netherlands. It's about an 86-meter long vessel, cargo vessel. And we tested 3 different configurations using a Flettner rotor of 3 meters in diameter and 18 meters in span. So we had 1 configuration with 1 Flettner rotor only, and 2 configurations with 2 Flettner rotors. One is called side, so the 2 Flettner rotors were at the bow on the side, one on the port side and one on the starboard side. And the last configuration is 2 Flettner rotors in line, so basically installed along the center line of the vessel and with a distance of 7.5 diameters. So from now on, just for the sake of brevity, I will only present the results of the 2 Flettner rotors in line. So one, let's say, behind the other along the center line of the vessel. Here is a plot of the aerodynamic thrust on the left, produced by the Flettner rotor. And P rotor is actually the power that you need to supply to the rotor in order to function. So this is for a vessel speed of 11 knots and for a true wind speed of 20 knots. And this is all the true wind angle. So we compare the aerodynamic thrust generated by the rotor without flap and with flap. So with flap, it's with the continuous line, red line, and without flap is the dotted line. So there are 2 things to notice. The first one is that using a flap actually increases the aerodynamic thrust of the Flettner rotor. This is the first very noticeable effect. And the second effect is a reduction in the tacking angle. So the tacking angle is basically when the aerodynamic thrust is larger than the induced hydrodynamic resistance caused by wind assistance, so caused by the use of the Flettner rotor. So you see here in this point where the red line becomes larger than the continuous blue line, which is the hydro resistance, and this happens at about 30 degrees. So this is the tacking angle for the case with flap. Without flap, the tacking angle is about 12 degrees larger at 42 degrees. You see it here where the 2 dotted line crosses. So there is an improvement both in aerodynamic thrust, but also in pointing ability of the Flettner rotor, of the ship equipped with the Flettner rotor with flap. Here you see the polar of what we call the polar of the vessel. So basically, in this case, the vessel is symmetric. So we only show, let's say, the one side. This is the fuel savings polar. So basically, we compare the ship with wind assistance, with the ship without wind assistance for the same wind conditions, basically. So in this case, again, the ship speed is 11 knots. The 2 Flettner rotors are in line, and we compare the standard Flettner rotor and the Flettner rotor with flap. So what you can see is that the 0 line and actually all the other lines as well are moving towards the left. So this is, let's say, from this vertical line towards until the 0 line is where the Flettner rotor is not able to produce any fuel savings because it's operating at a wind angle too much close to the wind direction. So it's basically the dead zone. But you see how this line, due to the flap, is reduced. So this is actually the tacking angle which is reduced. And also for all these other lines have moved to the left, meaning that the Flettner rotor is able to produce a larger aerodynamic thrust at smaller wind angles. So it improves the performance of the Flettner rotor, particularly in the upwind condition. So the last step that we took in our analysis is to look at the performance of the Flettner rotor of the ship equipped with the Flettner rotor with a flap and with a standard Flettner rotor when operating along a certain route. So we consider the North Sea region, particularly the routes between Rotterdam and Trondheim, from south to north, so from Rotterdam to Trondheim, and from north to south, so from Trondheim to Rotterdam. So here you see the wind rows. So basically the probability of occurrence of a certain wind speed and wind direction for this route, in this case, south to north. And if you go from north to south, actually, you should imagine the same condition, but with the wind coming much closer to the bow. So by multiplying this wind scatter, so this wind rows with the results that I show in this picture, so basically the fuel savings, we are able to estimate how much fuel the ship is saving when operating along this route when it's using the Flettner rotor with flap and the standard Flettner rotor. So the fuel savings from the route south to north for the rotor without flap was 15.3%, and when using the flap was 18.1%. So this is an increase of 18.3%. Whereas the route north to south, the ship with the two Flettner rotors without flap was 11.4, and using the flap is 15.1, which is an increase of 32.5%. So why? Well, first of all, it's a quite considerable increase in performance thanks to the flap. And you may wonder why there is a difference in increase. Why is it performing? Why the Flettner rotor with a flap it provides a larger going from north to south? So basically, it's because when you go from north to south for this route, you're sailing closer to the wind direction, so more upwind, and this is a condition in which the flap delivers the largest performance increase compared to the Flettner rotor without flap. So this is all from my side. So just a few conclusions. Adding a flap to the Flettner rotor can increase the lift to drag ratio up to a factor of 2. In terms of improvements on ship performance, having a larger lift drag ratio ensure that the ship can perform better in upwind condition, and we just seen it for the two routes we analyzed. Also, the flap ensure that the tacking angle is smaller, so the ship is able to operate to an angle closer to the wind direction. And in terms of fuel savings, we noticed that for certain routes, the performance increase delivered by the addition of the flap can reach up to 32.5%, which is a considerable increase. So thank you. That was all from my side.
Questions? Any details about how to build this flap? Actually attach it to a real ship.
Right here.
I didn't hear the question.
Great. The question was, do you have any details or thoughts on how you might actually build the flap itself and attach it to an actual rotor on a ship?
Yeah, that's a good question. I think it's, let's say the idea, it's an interesting idea. And it proves to give like a quite nice performance boost. But no, at the moment I wouldn't have an idea how to actually build the thing and actually install it on a real ship. I think it does provide some issues in terms of structures and in terms of let's say reliability of the system. So I think for the time being it's still, let's say, just a theoretical device.
Maybe an area for a future web thesis. Spencer.
I was wondering how you size the flap.
Question was, how do you size a flap? Right, chord length size for a rotor.
Yeah. So it was let's say we didn't do any very thorough study on the sizing of the flap. That is just to deliver, and as you saw in the presentation, it was like a very simple device, which is like a flat plate. The flat plate was about 30 centimeters wide, and the diameter of the Flettner rotor was 1 meter. So we assumed that like 1/3 of the chord of the diameter of the Flettner would be enough, let's say, to generate that separation that is needed to control the lift and drag. But we didn't do like any thorough study. And like in this case, basically, since the flap is detached from the rotor, The only thing that matters is indeed to create the separation.
Yes, absolutely.
Yeah, thank you. Do you see any disadvantage to using this? For example, any specific wind direction that you might be better off without it? Because it's like a win-win situation.
So, and disadvantage, if I heard, if I heard correctly, if there is any disadvantage of using a flap, well, I think, well, I mean, this is just one study, and indeed we did like a two-dimensional study in the sense that tip effects, because of the test setup that we use, were neglected. So that might change a bit the result. That's one thing to take into account. And the second thing is indeed that when you actually install a Flettner rotor on a ship, there should be a trade-off between the performance that delivers, the cost, the simplicity. So I think the main drawback of such a system is probably the complexity.
It doesn't really seem that complex.
Well, the wind tunnel is probably much simpler because indeed it was not attached to the rotor at all. It was just on a stand like on the floor. So it was not attached to the rotor at all. But in real life, I think it could be more complex.
Thank you.
Anything else? All right, well, thank you very much. Thank you very much, Giovanni.
Thank you.